All right, everybody, welcome back to another video. Today we're going to be looking at the derivative of log e of x. So how do we find this derivative? I'm going to show you two ways of finding this derivative. The first one is shorter. The second one's using the definition of the derivative. So in my first definition, I'm actually going to, my first proof, I'm actually going to use this result that we found in a previous video. So if we recall that the derivative of e to the power of x is in fact e to the power of x, we can actually use this fact as our proof. So let's just call this proof 1. So this is going to be my proof 1 for this video. And we want to show that the derivative of log ex is 1 over x. So let's just start by writing out what we have here. So we have y equals log e of x. And if we recall the definition of the logarithm, we can rewrite this expression. If we swap the way we write this around a little bit, this is actually exactly the same as saying that x is equal to e to the power of y. This is the definition of exponents and logarithms. This is the relationship between them. The power at the top is called the logarithm. So we can write these two expressions in exponential form, exponent form, or logarithm form. So these two things are equivalent. If we accept that these two things are equivalent, we can actually then take the derivative of this with respect to y. So what is dx dy of this expression? Well, what we have here, dx dy, what we have here is e to the power of y. So if we derive that with respect to y, we're just going to get e to the power of y. It's exactly the same as this result here. We derive e to the power of x with respect to x, we get e to the power of x. If we derive e to the power of y with respect to y, we're just going to get e to the power of y. It's the same thing. Okay, but we want dy dx. We don't want dx dy. So that's okay. We can just take the reciprocal. So if we flip this fraction, if we divide both sides, or maybe rather raise both sides to the power of -1, we're going to get dy dx on this side. And on this side, we're going to get, well, right now it's e to the power of y over 1. So this is going to become 1 over e to the power of y. And what is e to the power of y? Well, hang on a minute. E to the power of y, that's just equal to, let me change the color real quick. Well, why is this not working? That is actually just equal to, in blue, e to the power of y is equal to x. That's our definition right here, right? So e to the power of y is equal to x, so therefore 1 over e to the power of y is equal to 1 over x. And we're done. The derivative of log ex is 1 over x. Maybe that wasn't so satisfying though. So let's have a look at another proof. So this is going to be proof 2. And in this proof, I'm going to use the definition of the derivative. So you might need to recall that definition, which is that the derivative is equal to the limit as h goes to 0 for f of x plus h minus f of x over h. We're going to use this definition. So let's try this method. So first up, let's let the function f of x equal to log ex. Secondly, let's consider what each of these things are going to be. Well, the derivative, if we sub that into this definition of the derivative, we're going to find that the derivative function f dash x must be equal to the limit as h goes to 0 for log e of x plus h, that's the function with x plus h as the input, minus log ex divided by h. Okay, now what can we do with this? Well, the first thing we're going to do is see if we can simplify this a little bit using our logarithm laws. So the first thing I want us to recall is one of our log laws. If we have a logarithm and we take away a logarithm and the two bases are the same, so log e a minus log e b, for example, that's going to be equal to log e of a divided by b. So when we're dealing with logarithms and there's subtraction involved, we can divide the two things inside the brackets. So therefore, we're going to find, getting back to here, that the derivative is going to be equal to limit as h goes to 0 of log e of x plus h divided by x, right? So x plus h divided by x. And that's just simplifying things down just a little bit for ourselves. Okay, now what can we do with this? Okay, so from this step, we're going to see if we can write this in a slightly different way. What we can do is we can recognize, okay, if we have log e of something divided by h, that's the same as writing this as, well, that divided by h, that could be represented as 1 over h, right? So we could write this as h goes to 0, just make sure that's clearly an h, of 1 over h multiplied by log e of x plus h over x. This allows us to then use another logarithm law. So here's another log law that we're going to have to recall. If we have a constant out the front, and remember h is just a number, it's a number that's really close to 0, but it is just a number. So if we recall that if we have, let's say, let's say a log e of x, that is exactly going to be equal to log e of x to the power of a. So if there's a number at the front, we can bring it inside the logarithm. This is another one of our log laws. So let's apply this law right here. That tells us that the derivative, and again, let's keep the two proofs separate. So they're two separate proofs. The first one's just a rather simple one, which hopefully everyone could understand. This one here, the derivative is going to be equal to the limit as h goes to 0 of log e of x plus h over x raised to the power of the thing that was outside of the logarithm, which is 1 over h. Okay. Now, can we tidy this up at all? Well, we can see that that thing inside the logarithm, so that thing inside the logarithm, or inside the limit, I should say, that could be written, again, in a slightly different way. We can see that we have x over x. So x divided by x, that should just be equal to 1, provided that x isn't 0. That's most of the time going to be equal to 1. So we can take that as 1, and we can also take this part, h divided by x, like so. And hopefully we can see that that fraction there, if we have a fraction over a denominator, we can split that fraction, write it as x over x plus h over x, and that simplifies down to what I've just written right here. Okay, what else can we do with this? Well, now we're going to try and well, first up, let's have a think about this thing here. If you ignore the log part there, this kind of is getting rather close to the definition of E that we looked at in previous lessons. We've got a limit, we've got something happening over here. So it might be useful to introduce a change of base. So what we're going to do here, and I might do it in purple, is we're going to let a new variable, so let's introduce something else. I was going to let it be let it be n, but I might get the h's and the n's confused. So let's let it be let's say capital N, because we want n to be involved here. So I'm going to let capital N be equal to let's have it as h over x. Okay, so let's introduce it like this and see what happens. So therefore, the derivative, so I'm just introducing a bit of a change of base here. Let's write this in terms of everything here. So if we have h over x is equal to this, well, then we're going to have, that's just going to be n, right? This 1 over h, what will that become? Well, we can see here, if n is equal to h over x, h is simply equal to n times x. So therefore, 1 over h is going to be equal to 1 over n times x. So if we just take the reciprocal of that, 1 over h is 1 over nx. And we could also write 1 over nx as 1 over n times 1 over x. And you'll see why I've done this in just a minute. So let's write out this derivative now using these change of base that we've just introduced here. So we can now write, now I'm going to change things around. As h goes to 0, what's happening to n? Well, h is just equal to n times x. So as, n is equal to h over x. So as h is going to 0, n is also going to go to 0, right? They're both going to 0. So we can just write this in terms of n. So the limit as n goes to 0 of log e of 1 plus, okay, so h over x, that's what we called n. So let's just sub in capital N there. So log e of n of, okay, now 1 over h, that was equal to 1 over n times 1 over x. Okay. All right, so now what can we do with this? Well, let's look at this thing here. We have a power involving a logarithm. We can now use this law that we used before. The fact that a log ex, the one in blue here, a log ex is equal to log e of x to the power of a. We can use that in reverse. So we've got here these two powers. I'm going to bring this one that involves 1 over x out the front. So using what we know, this means that the limit as n goes to 0 of, now this thing in the brackets, that is now going to become, if I take that 1 over x out the front, 1 over x, then everything inside of that logarithm stays the same. Okay, check that out. So what we've done here is we have brought the 1 over x out the front using as the fact that log e of x is equal to, sorry, log e of x to the power of, we had a before, log e of x to the power of a is equal to a times log e of x. So because those two things are equivalent, we are allowed to do this. All right. Now, this is quite exciting. So the first thing we can do here is we can see that, well, we've got this 1 over x here. That 1 over x does not contain n. It's got nothing to do with n. In fact, it does not depend on n. So as n goes towards infinity, because that's what the definition means, as n goes to infinity, 1 over x is not changed. So we can actually just take that outside of the limit. It is not affected by the limit as n goes to 0. So this is just the same as what we've written here. Okay, and this is extremely important because what we can now do is we can look at this expression here. If we wanted to, we can introduce a third change of a base. In fact, I might do this just to show this to you. But this thing right here, so this expression here, the limit as n goes to 0 of this thing here, is exactly equal to e. In fact, I'm going to write this in a slightly different way for you, just so it's a bit more obvious. So again, this log e component does not depend on, it doesn't depend on x, it doesn't depend on n, sorry. We could flip the order of the limits and the logarithm here, and the expression is going to stay the same. So we're going to get log e of the limits as n goes to 0 of 1 plus n to the power of 1 over n. And this thing inside the logarithm is the definition of e. So I'll just prove that to you real quick. I'm going to, again, introduce a change of base. This time I'm going to use lowercase n. I'm going to say let lowercase n be equal to 1 over capital N. And what you're going to notice here is that if we introduce this, this 1 over n here is going to become lowercase n, and you can see that capital N is going to be 1 over lowercase n. So this derivative function, we're pretty close to the end here, this derivative f dash x is going to be equal to 1 over x times log e. Now, what does this thing inside the brackets here become when we introduce that change of base? Well, we can see that this is going to now be the limit as n goes to what? Well, if capital N is going to 0, then lowercase n, because that's 1 over capital N, if we have 1 over 0, that's like infinity. As n towards infinity, we're going to get 1 plus, so n, capital N is equal to lowercase n, capital N is equal to 1 over lowercase n to the power of n, and there we go. You can clearly see that that is the definition of e right there inside the brackets. So what we basically have shown is that that thing inside the brackets, inside this logarithm here, and I'll leave that as black just to keep things nice, that thing there is in fact equal to this thing right here is e by definition. So therefore what we end up with is 1 over x times log e of e. And if we have a log e, so the base is e, the thing inside the brackets c, what that's basically saying is e to the power of what's equal to e? Well, it's just 1. So that thing's just equal to 1. So what we end up with is 1 over x times 1. And 1 over x times 1, that is simply just equal to 1 over x. QED. That's another quick little proof of this. So you can take your pick which one of those you like better. The second one was a bit more rigorous. The first one was a little bit more simple and elegant, but they both show us the exact same result. And again, this is extension work. You don't need to know any of this. You just need to use these results. So you're simply going to be using the fact that the derivative of log ex is equal to 1 over x. But yeah, there we go. That's another little definition and a quick little proof. Next time, I think we might look at the product rule. So I'll see you guys in the next video. Hope you guys have a good afternoon and a nice long weekend. And I'll see you guys next time. Have a good one.